All right, last time we started section 9.2, we were talking about multi-stage experiments. One of the things that we mentioned last time, and let me re-mention it again, is that the work that we do in this section will have something akin to or likened to a tree diagram with most of our problems. And when they don't, they'll have some other kind of organized listing of things so that we're able to do our counting. So we had talked about tree diagrams looking like this second one here with the yellow on it. When we have multi-steps to it, it's a multi-stage tree diagram. And we did an example that was really kind of big and difficult because the probabilities changed every time. That doesn't always happen, but it did on this one. And when we got to this example number 2 problem, I showed you on this one something that wasn't a tree diagram, but it still did the same sort of thing. It listed all my outcomes out. I was able to count them up and so forth, right? Okay, so we're going to do an example now of a problem that has some spinners. It says, suppose an experiment consists of spinning the first spinner followed by the second spinner. It says, find the following, and it says a sample space S for the experiment. So a sample space is, as you know, a listing of options of things that can happen, right? So if I were to think about drawing a tree diagram for this, it's not super crucially necessary simply because of the way it's asking part A. But let me show you what it would look like in case that's not the question that we're being asked. We spin spinner 1, and we have a 1 or a 2 that can pull up. And because the spinner is split evenly in half, the angle through which it goes is evenly in half, each of those have a probability of 1/2. And then after I spin the first spinner, I spin the second spinner, and it has 3 outcomes, a 1, a 2, and a 3. And what's the likelihood of those outcomes? Yeah, they're all 1/3 because, again, it's evenly divided. So this is what a tree diagram would look like for this experiment. The reason I say that it's not absolutely crucial to draw a tree diagram for this is because as I do my sample space, I'm going to create equivalent work. The sample space has that curly brace. That's not one at all. Let's try that again. And for what we're doing here, it might be a good idea for us to use sort of an ordered pair kind of notation. In other words, I can spin a 1 on the first spinner and a 1 on the second spinner, or a 1 on the first spinner and a 2 on the second spinner, or a 1 and a 3. Also, I could spin a 2 and a 1, a 2 and a 2, or a 2 and a 3. And because over here, like we noticed, the probabilities along this branch are equally likely, 1/2, 1/2. Here, 1/3, 1/3, 1/3, all of them. We actually have 6 different outcomes that are all equally likely. In other words, if I were to multiply along all these branches, I'll get the same thing, right? 1/2 times 1/3, this is 1/6. 1/2 times 1/3, this is 1/6. They're all 1/6. And sure enough, I have 6 different outcomes. So just because I have 6 outcomes doesn't mean that my probabilities are all 1/6. But this one did because they were equally likely along the way. Right? Like if this spinner for the 1 and the 2 had been divided like 1/3, 2/3, I could not just make a sample space and say, hey, there's 6 outcomes, all equally likely. They wouldn't be equally likely at that point. But this one they are. So if on this one you only listed out that number, the numbers like I did there for the sample space, which is the answer to this particular part of the question, you'd actually have the right information because they're all equally likely. Now, we're going to look at a few questions based on the sample space, or you can do it based on the tree that we drew, either one. It wants us to find the probability of spinning 2 even numbers. So looking at my outcomes, I'm going to look at the ones that are in pink. What outcomes would count in that category? Just the 2, 2, right? It's the only one that has 2 even numbers that are spun. So there's only one of those outcomes out of how many? 6. If you're thinking in terms of the tree diagram, you can find it. It's down here. It's the one that goes 2, 2 down here. And again, if you multiply along the tree diagram's branches, you'd get 1/6. Second question says, spinning at least 1, 2. So that means any of them having a 2 in them. How many of my outcomes have at least 1, 2 in them? There are 4 of them. I've got 1, 2, 3, and 4. So there are 4 outcomes that fit that criteria out of 6, and 4 out of 6 is actually equal to 2/3. And again, if you were using the tree diagram, you would count every single one down here that has a 2 in it, which is all 3 of those lower branches, and the branch right here that has the 2 in it. You'd find each of their probabilities, which would be 1/6, 1/6, 1/6, and 1/6, and add them up for 4/6. The last question says, spinning exactly 1, 2. How many do that? 3 of them. Everything but the one I just erased, the 2, 2 outcome. There are 3 of those. So I have 3 out of 6, which is 1/2.
I'm confused on that one. Spinning 1, 2. Like, wait, can you elaborate how there's 3? I'm confused.
Okay, 1, number 2.
Yes. But, like, if I just spin a spinner and it lands on 2, wouldn't that be?
No, so do you see we got 2 spinners we're spinning?
Yes.
So when I do this experiment, I spin both of them.
Yes.
I could have both of the spinners land on a 2. I could have one of the spinners land on the 2, or I could have none of the spinners land on the 2.
Okay.
So the ones that are in pink are the different outcomes that could happen.
Yes.
So right here, I spin the number 1 and I spin the number 1 again. So I spin the number 1 on this spinner and I spin the number 1 on this spinner. This one says I spin the number 1 on this spinner and the number 2 on this spinner.
Okay.
This one says I spin the number 1 on this spinner and the number 3 on this spinner.
Okay.
So these are my outcomes of how my spinners can sort of land.
Okay.
Kind of like rolling dice. How do they land? Well, I have it either lands in a 1-1, a 1-2, a 1-3, a 2-1, a 2-2, or a 2-3. So as I'm counting up my ways of doing things, like on the last one here, if I want to have a spin that has exactly 1, 2, that means that we want one of these here to have exactly 1, 2 in them. So this
Okay.
one doesn't count because it had 2 2s in it.
Got it.
But the other 3 that are underlined in pink still have 1, 2 in them, so they still count.
Got it.
Okay? All right, let's shift gears. One more, another couple of examples. This one's kind of a fun one. I promise that this feels very true to life. I never actually calculated it. But when I purchase a new shirt for my son, there is a 0.15 probability he will stain it the first time he wears the shirt. I'm pretty sure it's higher than that, even now, as a 13-year-old, actually. He stained his shirt today when I took him to lunch. No joke. If the shirt is stained, there is a 0.2 probability that I will not be able to adequately remove the stain. Okay, so I scrub it and it doesn't come out. It's stained permanently. What is the probability that my son's new shirt will be permanently stained after the first time he wears it? Okay, so there's 2 different things that happen here. What's the first thing that happens that I'm comparing? Yeah, did it stain or not? So you're just going to write, you can actually write those phrases out. There's a stain or there is no stain. Okay, he wears the shirt. It's either stained or there's no stain. If it's stained, what probability is that happening at? 0.15. So then, what is the probability that there's not a stain? 0.85. And for those of you who didn't think about that immediately, what we're doing is we're adding these up to the number 1. So you're taking this number and subtracting it from 1 so that you find this number. These 2 numbers have to add up to the number 1. Now, the reason I do this example is because I want you to see that not all tree diagrams have the same number of branches. So this is one set of branches. But the reality is that if he doesn't stain his shirt, like if I'm in the lower branch, I don't have to scrub the shirt. Are you with me? Okay, so as I'm drawing my next set of branches, there's only one more set, and it's only on the stained part because that's the only one I have to clean. In the sense of scrubbing. Is everybody good with that? So it feels like I've got a lopsided tree diagram. You're going to have some lopsided tree diagrams and problems you're encountering as well. And then after it's stained, I have to clean it. And there's one of 2 things that could happen. What are they? Yep, it comes out. So it's really clean. or it does not come out. And obviously, there's other ways that you could write this. So if I scrub it, what's the probability that the stain comes out? What is it? Sorry. 0.2. And what's the probability that, I'm sorry, I said it wrong. That 0.2 is that it doesn't come out. It said it right here. That I will not be able to adequately remove the stain. So there's a 0.2 probability that it does not come out, which means what's the probability that it does come out? 0.8. Good. Okay, so the question is asked at the end says, what is the probability that the new shirt will be permanently stained after the first time he wears it? Where in the world will that allow me to land? Where am I? I mean, I've got three different ends here. I've got the first end, I've got the second end of my tree diagram, and I've really got a third end down here. Which end am I on if it satisfies that question? It's the second one. The stain happened and it didn't come out. So according to what we looked at last time, we multiply along the tree diagram branches. So this would be 0.15 times 0.2, which gives me what? Somebody get it? 0.03, you're right. So that's a 3% chance if we were thinking about percentages, but it's 0.03 probability. Emma.
Do we have to do like units or labels on these stuff?
There are no units for probability. Nope. It's a good question. All right, let's look at an example of a tree diagram that's like a family tree almost. Not exactly, but kind of. Joe says that if a family has 2 children, then the only possibilities are 2 boys, 2 girls, or 1 of each. Because there are only 3 possibilities, the probability of having 2 boys is 1/3. Is Joe correct? So he's doing something kind of like what we were arguing over here about my box in pink. He's listed out the outcomes. The outcomes include 3 things that he is specifying. And he's saying that they're equally likely. There's 3 outcomes, so it's a 1/3 probability for each one of them. Problem is, just because there's 3 outcomes for something, distinctly different outcomes kind of thing, whatever, does not mean that all the outcomes are equally likely, right? It doesn't. It did here because my spinners were evenly distributed, right? They were evenly divided up. So what we have to decide is if he's right based on his argument as well. So as we're thinking about it, you have a baby. There's 2 outcomes that are possible, right? One outcome is you have the child and it's a boy. Second outcome, you have the child and it's a girl. And how likely are each of those scenarios? Yeah, they're 50-50, right? So I haven't done one with decimals. I mean, I know the last one did, but one like this with decimals, so we'll use decimals on this one. You can use fraction if you want to. It's 50-50. Second baby. Okay, so no matter what happens with first baby, we are having second baby, and we have another set of tree diagram branches. Outcomes, again, are boy and girl. Boy and girl. And what are the probabilities along each of those branches? Yeah, another 0.5 along each of those branches. So, we want to know about the probability of having, which one did he say? 2 boys. Whoops. So we want 2 boys. So on my diagram, the way I've drawn it, the 2 boys is at the top, right? So what would I do? Multiply them. And what is 0.5 times 0.5? Yeah, it's 0.25, or if you're working in fractions, you would have gotten the number 1/4. So why is it 1/4 and not 1/3? All right, so Destiny, there's really 4 choices, right? Yeah. there's actually 4 different outcomes. 2 of the outcomes count the kids the same way, right? They have 1 girl and 1 boy. There's 2 outcomes that have 1 of each gender. But one of the outcomes, or that outcome is actually there twice, because it could be that the boy's older and the girl's younger, or it could be that the girl's older and the boy's younger, and so that's actually a distinctly different category that he's not considering in his calculation. So as we're sort of describing to Joe what's going on, let me give myself a little bit more space to write. We might want to say something like this. So Joe's incorrect. We'll talk about the way Destiny did. There are actually 4 outcomes, or 4. We'll say 4 possible outcomes. There's only 1 outcome, but there are 4 possible outcomes. You could also do them kind of like we did with our diagram over here that had the spinners, where you actually just listed them, right? So you could list them as boy, 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 girl, girl, boy, girl, girl. It's another way of listing those outcomes. So we do have the girl, boy showing up twice in the outcomes. So hence the probability of having 2 boys is actually 1/4, or you can say 0.25, not 1/3. All right, we're going to do a personal example from my life. Example number 6. Huntington's disease runs in my family. How many of you have heard of Huntington's disease? Is anybody? Got a couple hands. 3 of you. Huntington's disease is a very debilitating disease. It affects your central nervous system. It affects your reflexes and your ability to respond to stimuli appropriately. My grandmother had Huntington's disease and passed away it's been 15 years ago. In 2001, my parents decided to share with us that it was Huntington's disease that she had. So it was before she had passed away, but they told us about that. The probability that a child has Huntington's disease, if your parent has it, is actually 0.5. So my grandmother had Huntington's disease, and my grandmother had my dad is one of her children, and my aunt is the other one. So my dad had a 50-50 shot of having the disease, and my aunt also had a 50-50 shot of having the disease, kind of like our last diagram with the 50-50s everywhere for gender. It's a very hard disease. It can affect people at a very young age. It can also affect you at a very old age. And the interesting thing is that the age of onset for your parent determines your age of onset within 18 years of either side. For those of you who have had a little bit of probability, or not probability, but statistics, which we'll talk about later, it's a standard deviation of 18 years. So for instance, if my dad started showing symptoms at 40 years old, then 18 years younger than that, so 22, up to 18 years older than that, 58, I would be 68% likely that I would start showing symptoms between 22 and 68. So that's not very, spot on, like, 40, it's going to be pretty close to 40. It's not like that. So we were actually at home. My husband and I were living. We didn't have any children yet. We had been married for 3 years. My sister had been married for 1 year, and my brother was seriously dating the woman he ended up marrying. And we were living in Kansas at the time, and we were home for Thanksgiving. And my parents just decided to tell us, hey, this is what's going on with your family. Your dad actually has this disease too. My dad had been tested. He was actually tested in 1995, so my parents had actually known for quite some time before they decided to share the news with us kids. So I have 2 siblings, and if I have it, then I would have a 50-50 shot of passing it on to my children. And so I remember sitting in my parents' house that night and running the mathematics that I'm going to run with you here in just a moment in my head. And I didn't draw a tree diagram. We are going to draw one. But I did the numerical calculation that we're going to do. And what I really was trying to figure out in my mind is how likely is it that we all escape this disease? because it's really awful. The things that I remember about my grandmother related to the disease is I remember going to a place like a Golden Corral where you have like the self-serve ice cream like y'all do in the GC, right? And I remember her not being able to stop the self-serve ice cream and the ice cream going everywhere. I remember being in a car when she was driving longer than she should have been driving, and her reflexes not being able to stop the car in time at a stoplight before hitting the person in front of her. She wasn't going very fast, but her reflexes just didn't operate in that amount of time. So when we were, my husband and I, so we'd been married for 3 years at that point, and nobody had any children, my sister, myself, or my brother and his girlfriend at that time. But I sat there and we actually said, if I have this disease, we're not having kids. Period, end of discussion. And we made that decision right there that night. I would have been, let's see, so this is in 2001, I would have been 22 at the time. So I'd have been really close to y'all's age making that decision that I was never going to have children. And we made the decision right then, too, that I would definitely be tested for it. The reason that my parents shared this information with us at that time, as opposed to like before, is because in vitro fertilization had advanced to such a degree that what you were actually able to do is you were actually able to take an egg and a sperm, and you were going to be able to analyze them, create the embryo, and if they get 8 whatever big, they can actually take one of the DNA cells or whatever, and they can check to see whether it's going to have that disease. And my husband and I said, we're not going to do that. That's too much playing God for us. And so we actually did this math in our head and tried to decide in our minds, how likely is it, 50-50 shot for each of it, how likely is it that none of us is going to end up having it? So I'm the oldest, so this first branch is actually myself. And there's 2 choices, right? I either have it or I don't. And it's a 50-50 shot. I'll do fractions this time. In case you're wondering, I definitely did fractions in my head when I did it too. I don't do decimals in my head very, very often. My sister is the next. So this next set of branches actually represents my sister. And again, she either has it or she doesn't. And again, it's a 50-50 shot all the way along. 1/2 all the way. Or 0.5s if you wish. And then my brother is the youngest. So all these tree diagram pieces here at the end represent him. And it's either have or don't. And all the probabilities along the way are 1/2. So the question that I asked myself, yes, Gracie, sorry.
I'm just confused because like it looks like they're your children. Does that make sense? Like it's just not. This is not adding up in my brain. Like if you have it or don't have it, like then you have kids, and let's say you have it, and then they have it or don't have it. But these are your siblings, not your children. That's like hard.
So this diagram is not representing subsequent generations, but you could do a diagram like that. This diagram is representing just the outcomes that are possible if my brother, my sister, and I were to all go get tested.
Okay.
So if we were going to get tested, I have a 50-50 shot of getting a test back that says you have it or you don't. My brother has this, my sister has that same possibility. She either has it or she doesn't on her testing, and my brother either has it or he doesn't on his testing. Okay? 50-50 each time. Yep, Katie?
Would your sister having it depend on you having it?
No, absolutely no effect, which is why you see the 1/2, the same study throughout the entire thing. Yeah, there's no effect. So one child having it is no indication of whether the next one would. Emma?
So is this like writing you 3 up in order and saying yes, no, no,
Yep.
yes, yes, yes?
Exactly. Very much like that. It would be like taking a true-false test. If you have three questions, right? True-false. You have two options on each one of them. We have a 50-50 shot at getting the first question right, 50-50 shot at getting the second question right, 50-50 shot at getting the third question right. So there's 8 different outcomes that you could get in terms of getting the questions right or wrong. So they're all 8 at the end.
If you were to have 2 children instead of 3, you'd be more likely to have it?
No, I'd still have 50-50 shot, but they would be less likely or more likely potentially to have more or less of their children with it in the end. It's kind of like, if you looked at if you examined all 2-children family, you'd probably find very much more frequently that you have 2 boys or 2 girls than if you examined a 6-person family and you found that they had all 6 girls or all 6 boys, right? The outcomes change just in terms of everything being multiplied by 1/2 every time to get those specific outcomes to line up. So what I did in my mind that night is I looked at this particular piece down here, which is answering the question that's being asked. What's the probability that all of us are clear? None of us have it. So what is the probability that none of us have it? What is 1/2 times 1/2 times 1/2? So I'm answering a slightly different question from part A. What's the probability that none of us have it? What does that give me? 1/8. And if you are doing decimals, you're getting a 0.125. Okay? So if it's a 0.125 or a 1/8 probability that none of us have it, then what would be the probability that at least one has it? Yeah. So it would be everything else. Every other branch except for that last one that I circled in the pink, every other branch has somebody with the disease. They have the have. Whether it's me, my sister, or my brother, every other branch. And so it's 1 minus the 1/8 or 1 minus the 0.125. And you're right, it's 7/8 or it is 0.875. That's the number I came up with in my head. 87.5% chance that at least one of my brother, my sister, and I, one of us at least, will have this disease. And that's the outcome where I said, that's really high, right? That's really, really high that one of us is going to have this. And so my husband and I said, we're not doing it. We're not passing it on to a future generation. So it was right then and there where we said, if I have this disease, we're not having kids and we will adopt. So in 2003, 2 years later, Thanksgiving actually as well, I concluded my testing. It's actually a several-month process to get tested for this disease, including psychological testing along the way. And I don't have the disease. Because I don't have the disease, I have my daughter, Abby. Otherwise, we wouldn't have had any kids. But because I had to go through that in that 2 years, we knew, beyond a shadow of a doubt, before we got through that testing, that we were supposed to adopt anyway. It was going to be part of our story. So 2.5 years after we had Abby, I finished grad school. And we moved to my first teaching assignment, which was up in Ohio. And within 2 days of entering Ohio and having our permanent address, we emailed off paperwork. It wasn't even email. I would think it was snail mail, but off paperwork with money to adopt from Ethiopia. Because God had just opened our hearts in a way that was so clear to us that this is what we were supposed to do. And as a result of having Eli, we ended up having Temesgen and Lelise. Some of you know them here as well from Ethiopia. Also, just an aside to this, as a result of 3 years ago, Monday, 2 days. So 3 years and 2 days ago, I posted the cutest announcement ever that I was pregnant online. It was super cute. It was 6 little safety pins, and there was a baby safety pin inside of the mama safety pin. It's adorable. And it's in my news feed, right? I can see it in my memories on Facebook because I was pregnant. And about 6 weeks later, I miscarried. And, God took us through another time of saying, well, what are we going to do with this information? Just like he did here. And we really felt very clearly that he was saying, I have something else in store for you. 4 is not going to be where you're going to stop. And we have 2 additional kids right now, as you guys know from my pictures early on, that I never speculated would be a part of my family. And you guys are the first ones to hear that we're doing it again. We have 2 more that we're in the process of bringing over from Ethiopia, a girl and a boy. They're 13. I don't know how long it'll take. We've taken anywhere from a few months to a couple years, but we're in the process to do so again. So what I wanted to say kind of as a thought to conclude that before we just do this real quick little problem here at the end is that the hard stuff brings about some of the most amazing stuff in your lives. My heart was always soft toward adoption to begin with when I was a teenager and so forth and new families. But God definitely used that time of Huntington's disease and the horrible nature of all of it to bring us to a decision of what he wanted to do with our family. As of even today, my brother and sister still have not been tested. My brother is 38 or 39, and my sister is 41. I think that's right. I think they're 39 and 41. So in this diagram over here, what we actually know right now is we know that this part of the diagram, hang on while I get this cut out, can't happen because I don't have it. So I eliminate that entire set of branches, and the set of branches that still are possible are right here at the bottom. So the second part of this question pertains to just that set of branches, my brother and my sister and my brother actually. And I can rerun the same set of questions that I did before. What's the probability that at least one of them has it? Well, the probability that they both do is 1/2 times 1/2, or 1/4, or if you prefer 0.25. So the probability that they both do or they both don't, either way, we'll say both don't. So the probability that at least one does is 1 minus that. So there is still a 0.75 probability that one of my brother or my sister does, and they do both have children. My sister has 3 children, my brother has 2 children, and again, the branches will extend and they will continue if in fact one of them has the disease.